Good morning, all of you. This is Nageswara, Assistant Professor of Physics, SRR Severe Government Degree College, Vijayawada. Today, in this presentation, we will discuss about node voltage method. Before understanding the node voltage method, we want to remember Kirchhoff currents law, that is Kirchhoff first law. Because the Kirchhoff first law is compulsory before entering into the node voltage method. What is Kirchhoff first law? We know Kirchhoff first law is also called Kirchhoff currents law. It states that the algebraic sum of the currents at the junction is zero. In another way, we may say that the sum of the currents entering to the junction is equal to the sum of the currents leaving from the junction. For example, in this diagram, this is a junction. Two currents are entering into the junction, that is I1 and I2. And three currents leaving from the junction, I3, I4, and I5. So this is one of the simplest example of our socket in our house. In our house, from a single socket, we are connecting TV, telephone charger, and any other electronic instrument or electrical instrument. In such cases, how can we calculate currents I3 or I4 or I5? Then for that case, we can use this Kirchhoff first law. When we apply Kirchhoff first law to this junction, that is I1 plus I2, that is current entering into junction. So I1 plus I2 is equal to sum of the currents leaving from the junction, that is I3 plus I4 plus I5. So this is called Kirchhoff first law. Now, what is voltage method? Node voltage method. What is its importance? The importance of this node voltage method is to calculate unknown voltages in a network. Now, let us assume there is a two closed networks, that is 1 and 2, in which one power source is we are using, and 5 resistances R1, R2, R3, R4, and R5. In such cases, we can calculate voltages at nodes. How much voltage is at A, how much voltage at B, how much voltage at C. Now, we can write by using the Kirchhoff first law, there is a number of equations, that is current equations by applying at A and at B junction, at a C junction. By solving these equations, we can calculate potentials. Now, from this diagram, there is 5 resistances and 1 power source, that is 2 loops and 1 power source. So in such cases, how much current is passing through the resistance R1 and how much current passing through the remaining resistances? Because to apply Kirchhoff first law, how many currents are passing? We know when we apply at junction A, there is a R1, that to which the current I1 is entering into the junction. And here I2 is leaving from the junction and I1 minus I2 is also leaving from the junction. Now, what is the magnitude of I1? What is the magnitude of I2? What is the magnitude of I1 minus I2? When we apply that is Ohm's law, according to that I is equal to V by R, where V is potential difference. Now, in this resistance R1, the potential difference across this resistance is E minus V1. Now current I is equal to E minus V1 by R1. That is current which is passing through the resistance R1. You see, that is current passing through the resistance R1 is E minus V1 by R1. And the current passing through the resistance R2, where the potential difference is V1 minus V2. And the current passing through resistance R2 is V1 minus V2 by R2. You see here. And current passing through resistance R3 is potential difference is V2 minus E. So that I1 is equal to V2 minus E by R3. Is here V2 minus E by R3. And the current passing through resistance R4 is the potential difference here is V1 minus V3. So current is V1 minus V3 by R4. Yeah. The current passing through resistance R4 is V1 minus V3 by R4. Similarly, the current passing through resistance R5 is I2 is equal to potential difference is V3 minus V2. So that V3 minus V2 by R5. These are the current components which are flowing through resistances R1, R2, R3, R4, and R5. Now we may apply Kirchhoff's first law to the junction A, or maybe node A is current entering into the junction, that is I1, that is equal to E minus V1 by R1 is equal to, leaving from the junction, that is at this place, V1 minus V2 by R2, and at this place, that is V1 minus V3 by R2, R4. Now by simplification, that is V by E by R1 minus V1 by R1 is equal to V1 by R4 minus V3 by R4 plus V1 by R2 minus V2 by R2. Of course, there is a three V1s are there when V1 is taken as common. E by R1 is equal to V1 into 1 by R1 plus 1 by R4 plus 1 by R2 minus. There is only two terms, that is V2 by R2, and here is minus V3 by R4. That is taken as equation 1. Now we apply this Kirchhoff's first law to the second node, that is B. You see here, there is at B, there is two currents entering into the junction, that is V1 minus V2 by R2. And here is at cross R5, V3 minus V2 by I2, R5. So that is here V1 minus V2 by R2 plus V3 minus V2 by R5. That is equal to current leaving from the junction, that is V2 minus E by R3. By simplification, this V1 by R2 minus V2 by R2 plus V3 by R5 minus V2 by R5 is equal to V2 by R3 minus E by R3. From this, E by R3 is equal to V1 minus V1 by R1 plus V2 by R2 minus V3 by R5 plus V2 by R5 plus V2 by R3. Of course, V1 is only one, that is E minus V1 by R2 plus V2 is taken as common 1 by R2 plus 1 by R5 plus 1 by R3 minus V3 by R5. That is equation 2. Similarly, Kirchhoff's first law can apply to the junction C also, where only one current is entering into the junction and only one current leaving from the junction. So that V1 minus V3 by R4, that is equal to V3 minus V2 by R5. That is the third equation. By solving these three equations, we can determine the voltages V1, V2, and V3. Of course, for easiness, these two equations can written as simply, that is I1 is equal to, from this equation, we know E by R1 is current I1 is equal to V1 into, where Y1 by R1 plus 1 by R4 plus 1 by R2, we know 1 by R, that is reciprocal of the resistance, that is called admittance. So this 1 by R1 plus 1 by R4 plus 1 by R2 is replaced by Y11, where Y11 is called admittance of the node 1, plus V2 into 1 by R2 is replaced by Y12, and V3 into 1 minus 1 by R4 is replaced by Y13. Similarly, the second equation can be written as E by R3 is equation I2 is equal to V1 Y21 plus V2 Y22 plus V3 Y23. So by solving these two equations, we can determine the potentials, where Y11, Y22 are called admittances of node 1 and node 2 respectively. And the remaining terms Y12, Y13, Y21, and Y23 are called mutual admittances of nodes 1 and 2, 2 and 1, 1 and 3, and 2 and 3 nodes respectively. Of course, this method is only applied to the two loads and one power source. Of course, this theorem is can apply to the n number of loops and also n number of sources also. Let us assume there is n number of loops and two power sources in it, two loops in a network in which there is V1, V2, V3, V4, and some VNR node voltages or junction voltages. Then the above equation can be written as I1 is equal to, for the first node, V1 Y11 plus V2 Y12 plus V3 Y13 and so on plus Vn Y1n. For the second node, I2 is equal to V1 Y21 plus V2 Y23 plus V3 Y23 plus so on Vn Y2n. We know in the third loop there is no current source, so that 0 is equal to V1 Y31 plus and so on. And also for the nth loop, 0 is equal to that one. By solving these equations, we can determine the voltages V1 to Vn easily. Here Y11, Y22, Y33, and so on, Yn and R admittances of the nodes 1, 2, 3, 4, and so on, respectively. And Y11, Y13, Y14, and so on. Similarly, these are called mutual admittances of corresponding nodes. For example, Yij is called mutual admittance of the combination of the nodes I and J respectively. So this is the method of node voltage method to determine the voltages in any network. Thank you.